Hello everyone. Can you listen to me? Hello, hello. Can you listen to me? Please reply in chat. Can you listen to me? Hello, hello, hello. Can you people listen to me? Okay, thank you. So today we are going to have a discussion on basic algebra. So let us start with some kind of small motivation for algebra. So 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 consider this equation: x plus 5 equal to 0. Fine. Now, if you think of this equation and if you try to solve it, um, so what we do is everyone would say immediately x is equal to minus 5. Now, can you see? Everyone would easily say it is x is equal to minus 5. Now, what happens here? Let us uh, see. So, x plus 5 equal to 0. What we do is uh, we are trying to search of a number which when added what happens is it gives back something called we will for now name it as 0. What happens is we are searching for a number which when added on both sides gives the left hand side to be 0. Fine. So x plus 5 plus minus 5 plus, so better I will write it as equal to minus 5. Fine. Now adding this is same as adding meter. So now, so this adds up to 0 and gives me minus 5. But x when added with 0 gives us x. So this will be equal to minus 5. So think of this carefully. We have actually defined the properties of a group. So we had an equation x plus 5 equal to 0. We are searching for a number which when added gives us something called 0. So it is called the inverse. So it was minus 5. When added on both sides, it is the same. Now we use the law of associativity, which we are going to define very soon. So we switch the brackets, which doesn't matter here. And we got a number which when added with it gives back the same. So now it ends up with h is equal to minus 5. So now we'll define the basic structure group. So what happens is, let us consider a non-empty set. Let this be the set. Now consider an element here and consider another element here. We are trying to relate these two elements and get a new element which lies again in the same set. That is, we are taking two different elements in the set. We are somehow trying to give a relation between them, and the result which you get must be in the same set. So what we are going to do is, we are going to define something called a binary operation. So star will be a function from g cross g to g, defined by star of a comma b. So every element in g cross g will be of the form a comma b, where a and b will be in g. So we are taking two elements and we are defining it to be a star b. And if this happens to be in g, that is by definition of function, then this function is called a binary operation on g. And this is what you call as closure property also. So binary operation and closure property means the same. So whenever you define something as a binary operation, it is not necessary to check closure. Now let us move to the next property. So now you have a non-empty set along with the binary operation star. The first one is closure, which says that given any a comma b in g, you must have a star b in g. That is, take to any two elements, try to do a operation between them, a fixed operation. It gives back an element in the same set. Now the next property is associativity, which tells us about how can you do the operation. So take any three elements in G. Now if we operate the second and third element, and we will get a byproduct D. Fine. Now operate A with D, you will get a result. Now this is the same as operating A with B, you will get some other byproduct, say some E, then with C. So this will be equal. That is, associativity refers to switching of brackets. That is, you can do the operation anyway if you have three elements. So please chat if you have any clarifications. Right? Now, next we are in search of a particular element in that set which, when operated with any element in A, gives back the same. So take any element A in G, we call that element, we denote that element as E. So A star E and E star A anyway must be equal to A. Right? So let us, after completing the fourth property, we will try to illustrate everything with an example. Right? Now the fourth property is inverse. So existence of inverse. Now let us consider an element in G you must find some other element B in G such that A star B and B star A must give us back the identity. It is something like pulling back. So you are going to operate with an element which pulls back it to identity. Either way, if we do, fine. Please note that this operation, when we do both the ways, that is A star B and B star A, need not be equal always for every A and B. Right? If suppose it happens to be equal, if suppose it happens to be equal, then that property is said to be commutative property. And if a non-empty set along with some binary operation satisfies the first four, then G along with star is set to form a group. And if a group satisfies this commutative property, then G comma star is called an abelian group. So this is just an introduction. So if you have any clarifications, please mention it in the chat. Or if we can proceed, we will try to illustrate with an example now. Is it fine, everyone? Can you see the board? Can we move on? Okay, we'll move on. Now, so what is the basic number system we have in our hand is the set of all natural numbers. Along with, we will consider the operation to be addition. Fine. Now, let us check whether it satisfies all the axioms of a group. So take any two natural numbers. Fine. Clearly, their sum also belong to natural numbers whenever A comma B belongs to natural numbers. So when you add any two natural numbers, it is going to again result in a natural number. Now, so the first property is satisfied. Fine. So maybe we'll make a checkbox here at the down. For first one, first property, second, third, fourth, fifth. So if it satisfies, I will put a tick mark. If it doesn't, we will put a wrong. Right? So n comma plus satisfies the closure axiom. So fine. Now associativity. So addition A plus B plus C and A plus B plus C. So even when you add up this two and add with this, or add this two and this, they are going to be the same. So associativity is actually a property of the binary operation defined. So depending upon the binary operation, associativity may or may not be satisfied. It depends upon the operation given to us. So here addition satisfies associativity. So fine. Now the third operation which we went into is identity. So we are in search of an element, say sum b, such that whenever you take any element in G, so we are searching B in G. Sorry, here G is natural numbers. So we are searching for a natural number such that given any natural number A plus B must be A. Okay. So now, if can you think of an element in natural numbers which gives back the same element? No. So what happens is natural numbers, when added with another natural number, it it moves on, it increases. So you cannot be at the same level for any natural number. So this does not satisfy the axiom of identity axiom. That is, it does not have an identity. So we need not check the other property, that whether it has an inverse or not. But let us check. So the fourth one, inverse. So do we need to check the inverse? The answer is no. The reason is it does not have an identity at all. The inverse property depends upon what our identity is. So we need not check the inverse property if the set and the binary operation does not have an identity. So inverse will not be satisfied. And the last one, commutativity, is a property of the binary operation defined to us. So for any given a and b, a plus b and b plus a are the same. So it satisfies the axiom. So natural numbers along with addition operation does not form a group. And it satisfies only closure and associative, but it does not have an identity and it does not have an inverse. Okay. Now let us move on to, let us just switch the binary operation and let us try. So we'll consider the same natural numbers and consider the operation to be subtraction. So let us check whether closure properties, whether subtraction is a binary operation on natural numbers. So what must be satisfied for any given a and b in n, that is for any given natural numbers, any two natural numbers, a minus b must be in n. Fine. Now, for example, consider some natural numbers, say 1 and 2. So, according to the result, according to the closure axiom, 1 minus 2 must be a natural number if it satisfies the closure axiom, or if subtraction is a binary operation on natural numbers. But 1 minus 2 is minus 1 in the general number system, and this does not belong to natural number. So we have found an element 1 comma 2 in natural numbers for which 1 minus 2 does not belong to n, and hence it does not satisfy the closure axiom at all. It does not satisfy the closure axiom at all. It fails in the closure axiom itself. Now, hold on. So we have found an element 0. There is 0. Now, so since identity exists, take any two. So we can even consider the example which we took, which gives us 0. Are you here? Is it streaming live? define. It is not in whole numbers. So we move on to the next now. So this will form a group. Fine. Now, so after we check whether it forms a group or not, so since this forms a group, we'll move on to checking whether it is an abelian. Fine.